Hello and welcome back to Calculus 3, section 16.3 on double integrals in polar coordinates. So let's sort out some of the stuff we have done so far so we know where we are in a map of integration. So we started with area under the curve, which was integral a to b of f of x dx. And then we upgraded to two functions, integral a to b f minus g dx, area between two curves. From there, we went to rectangular region integral over region R. That was calculating volume if we have double integral over region R for our function xy dA, and it was calculating area of region R if we did not have f inside, but the region was a rectangle. And then we went in the last, so this was 16.1, this was Calc 1, and this was Calc 2. And then we went and said, well, you know what, we can have any kind of a region. So let's say you have half a circle that goes into something like this, let's say. So now this is your region R, and in this case we had volume given as integral f of xy, and then this was dy dx if this was a and b, and these were the functions g of x and h of x. And we also had the area of the region only, same a, b, g and h, but just dy dx. The goal for today is to, let me just separate all of these. So there's one, there's another one, there's another one, and this was our 16.2. So today in 16.3, polar domain, polar region, and this is where we want to integrate when we have circles and flowers and all of the other things that we can get in polar coordinates. So before we do any crazy shapes, let's discuss the easiest, which is elliptical paraboloid, which is, let's say, the Taco Bell. Let's say goes through, I don't know, 9, whatever. And then these are 3s. So elliptical paraboloid. You see, our base over here is a circle, and if it's a radius 3, we have x squared plus y squared equal to 9, but when you go into polar coordinates, equation is simply r equals to 3. That's really cool. If you are in a polar domain with a circle, radius 3, you will draw what I call a representative pizza slice d theta. And you can calculate, the area of the circle and so on using Calculus 2 polar integration. But what we are interested here in is how to calculate the entire shape. You see this z over here, which is f of x, y, has a formula of 9 minus x squared minus y squared. And if you want to set this up in rectangular coordinates, holy nightmare, this integral is annoying and terrible. Really terrible. Because if you want to use 16.2 method to solve this, the volume will be equal to double integral negative 3 to 3 negative square root of 9 minus x squared to positive square root of 9 minus x squared. And then you have to have 9 minus x squared minus y squared in here, and then dy dx. This is what the integral for that function would look like. And that's just insane to solve, because you have to go and do all the trig sub, and it's not fun. It's not fun. Is there a way to transform this into a polar integral? Because polar integrals love working with those with circles. And the answer is obviously yes. We can transform this integral into a polar double integral, and it's going to be so easy, because polar double integral will have something over here, r d theta. Well, actually, this is now new, so we have to talk about it. So your function f of theta, well, f of r theta, will go in here, and then your angle alpha and beta goes on the outside for d theta, and then inside you have the radius that either goes, well, I'll just put a and b inside. I should have done this part better, but we'll see this. So now I see that I can actually convert all of this into this double integral. I should have done this. There we go. So double integral, and this equation now becomes 9 minus r squared. And then I have r dr d theta. So the conversion is, you can factor out minus sign, and it becomes, right, from the negative x squared minus y squared, you factor out negative, you get x squared plus y squared, and in conversion that becomes negative r squared. because x squared plus y squared equals r squared in a polar conversion. We learned that day one, reviewed it day one. So that's how I get negative r squared here. And now look at my limits. Limits are a joke. My radius, when you look at this d theta representative slice, I'll draw another one here and then I'll erase it. So if I take a look at my representative d theta, right, always the one that it's at the end is the representative. So representative pizza slice. In order for me to see what angles we're going to use, well, we're going to use the full circle. It's not, right, you can have half if you want to, but we want the full circle. So theta is going from 0 to 2 pi on the outer edge because of the full circle. And then the length of the pizza slice is going to be from 0 to 3 because that's the most it can stretch out. Well, this integral now just became a joke in comparison to what we had before. Because all you have to integrate now is the double integral, 0, 0, 2 pi, and 3. And you have over here 9r minus r cubed dr d theta. And this is a very quick integration. No trig substitution, none of that stuff. So 9r squared over 2 minus r to the 4 over 4, computed from 0 to 3, and I still have d theta to deal with once done with the r's. So 0 to 2 pi, open parenthesis, plug in 3, that's 981 over 2, minus 381 over 4, d theta. This is further equal to 81 over 4, kick it outside, 0 to 2 pi d theta, which is 81 over 4 theta, computed from 0 to 2 pi, plug in 2 pi, we get 81 pi over 2 minus 0, and that's it. So we got 81 pi over 2. If you are to use the x and y after 3 pages of trig sub, you will get the same answer. Yes?
Explain how you got the limits from 0 to 3.
Yes. So this is the basic calculation, and I hope you guys see that this is much simpler than cranking 2 trig subs, because we had that square root of 9 minus. Now, the question on the floor is the limits. And I'm going to work this one more time. So, if I have a full circle in a base going from, say, 0 to 5, and I can put the representative pizza slice here, d theta. When I am setting up integral, some blah over here, r dr d theta. I need limits for theta. So if I am using the entire shape, it will go, this representative d theta will rotate, it will start on x-axis, and it will rotate full 2 pi, so 0 to 2 pi. If you only want the third quadrant, which is this quadrant here, if you only want the third quadrant, then it rotates from pi to 3 pi over 2. So whatever slice you want, right, you will have opportunity to take just that slice of the pizza. But let's call it now 0 to 2 pi to go on. Now, the radius inside, that's this integral. You see, the trick is to swipe the entire area here and to color in everything as this d theta should be this d theta should be everywhere, right? Now the trick is that the d theta has to go all the way out from 0 all the way to 5. So that's why it's 0 to 5. If I had elliptical like this, but it had a hole in it, then your domain would look like this. And your d theta would be here. And let's say that this is 4, and let's say this is 2. So now your double integral of blah, because there will be some function there, r dr d theta, we're only talking limits now, so blah is just fine. If I want the full circle around, it's still 0 to 2 pi. But now the middle is empty. So it goes to 2 to 4. Exactly. It goes 2 to 4. So if you have an object that has a hole through it, you are not going to start at 0, because from 0 to 2 there is no material. It's empty. And then the material, the plastic or metal or whatever, is from 2 to 4, which is why we only take 2 to 4 in consideration for the radius. Make sense? All right. Can we have weird stuff happen? Of course. But that's the second part of the lecture, right? This first part is all about figuring these two basic concepts. Concept number one is, do you want the full shape? Or maybe you just have half of it, in which case half goes from 0 to pi, or from pi over 2 to 3 pi over 2, depends which half, right? Or quarter, you will again play the game of chasing which angle. Maybe you want the one pizza slice, which is 0 to pi over 4, or whatever slice. And then the radius is the second piece of the puzzle. Now, these guys cannot be rearranged. They're always in the same order, right? So you leave it there. So let's take a look if they have some nice homework assignment question.
That's a question.
Yes.
Are you going to get over to, instead of, because that past one was a circular paraboloid, the base was circular, are you going to get to an elliptical one?
No, you won't.
So we are not going to see those?
Can't integrate those.
That's what
Those are really nasty.
Okay.
They are very nasty calculations. So they will actually ask you if there is a question with the ellipse on the homework. It has that blue T next to the problem number, and the blue T stands for technology. So you have to use some software to integrate that. There is no integrating.
Yeah. You can't even really set up that.
Yeah, they're really, really crazy tough. So here is a cone question, right? You have a cone, and the equation for the cone is z equals 4 minus square root of x squared plus y squared. And they're looking for the volume. That's all you're given. So you can go and immediately, using the level curves, you will go and you will figure out what these values are, because you need to know the radius for this circle. Now that happens on the floor, and the floor over here is z equals 0. So when z equals to 0, you have 0 equal to 4 minus square root of x squared plus y squared. That's the square root of x squared plus y squared is equal to 4. When you square both sides, you get x squared plus y squared equal to 16. And from there, you know that radius is 4. Therefore, these are 4s. That's not given on a picture. You just know because, again, the level curve, that will be the actual largest circle that sits on the ground. The level curve there is z equals 0. So z equals 0. You plug 0 into the equation for the cone you have up there, and it's going to spit out that the radius is 4. So once you have that the radius is 4, you can set up your polar integral rather than messing with the circles and square roots and all of that stuff. So volume is going to be double integral, and you are starting, well, let's plug in the function first. So it's going to be 4 minus square root of r squared. Because anytime you see x squared plus y squared, you are replacing that immediately with r squared. And then you have the r, d theta. Guys, this is a string that is not changing ever. It stays that way. You always put it on at the end of the integral. And once you see this d theta, you know that the first integral is asking for limits that are angles. So I want the full cone, so 0 to 2 pi. And the calculation we did earlier, r is equal to 4. There are no holes in this cone. Therefore, 0 to 4, we want the entire cone. Now, square root and square will cancel. So this problem simplifies into double integral of 4 minus r times dr d theta. And finally multiply by that r to get the problem in its simplest form so you can integrate. So now you will integrate r, that's 0 to 2 pi. By the way, this is problem 11 in your textbook. I didn't mention that, but when we integrate r, we get r squared, no, we get 2r squared minus r cubed over 3, calculated from 0 to 4, and we still have d theta to deal with. So 0 to 2 pi, plug in 4, 1632, minus 64 over 3, and then minus 0, that goes away, d theta. Now we have times 3, that's 96, minus this is 32 over 3, kick it outside, and then d theta, 0 to 2 pi. So 64 pi over 3 is the, now because the integral turns into theta, you plug in 2 pi, so it's 32 times 2 pi, that's 64 pi over 3. So that would be the solution looking at these for polar integrals. Polar integrals are also good in some cases when you get something that you really can't integrate well. I'm just going to go with blah over here on the limits. I can just put region R, whatever it is. You have e to the x squared plus y squared dy dx, let's say. So you're looking at this integral, and you know that you cannot integrate e to the x squared, e to the y squared, because we first integrate in terms of y. You know you can't integrate because there is no y in front for u sub, and it's y squared up there. So there is no way to do this problem, right? There's no way to do this problem. You're staring at it and you say, well, I can't integrate in terms of y because if I'm integrating in terms of y, e to the y squared, I need y over here for u sub. Or I need something else to do by parts, or, you know. But then you say, x squared plus y squared is r squared. If I toss this integral in a polar domain over the polar region R over here, let's call it PR, polar region, you are going to get e to the r squared. And look at the string, r dr d theta. The string introduces r, and now you can do u sub. Problem saved. Now we can do u sub. Now we can u sub. So in this case, casting turning or transforming the problem from rectangular into polar domain made something that was impossible to integrate into something that is possible to integrate because we have r squared and then there is r here, and we can do basic u sub and solve the problem. Yes?
Wouldn't that make it a pain in the ass trying to find the limits, though?
No, because you are going to have, I mean, first off, you could have tough limits, but if you have no other options, you just have to deal with that, right? It's not that this was inconvenient. It was impossible, right? There's a difference between the convenience and impossible, right? It's impossible for you to fly. It's inconvenient, right?
Can you go over an example where we are changing the limits?
Well, we are going to. Well, actually, yeah. Why not? Let's just have a problem. So this was just illustrating. Cool, but here is. Let's pick this one. Problem 27. They give you -1 to 1, and they give you negative square root of 1 minus x squared to square root of 1 minus x squared, and they give you the formula x squared plus y squared to the 3/2 dy dx. As soon as you see circles in limits, as soon as you see x squared plus y squared, that immediately screams, transform me please into polar coordinates. Your job is to look at the limits they gave you. You know what, I don't like these limits. Okay, we have another, we'll do one more example. This one is too easy. So we have radius 1, right? Because it goes from -1 on x to +1 on x, and it goes from the bottom negative square root to the top positive square root. So it's a full circle they want. So now if I'm transforming this into my double integral for polar, I have my x squared plus y squared, well that's my r squared, and then I need to put that on 3/2. And then I have r dr d theta. This is one unit that you have to. This is the unit that replaces dy dx. And then you look at the circle and you say, they want the whole thing. So 0 to 2 pi, 0 to 1 on radius. They want the full circle. Make sense? And then we have r squared and over 2 cancels, so it's just r cubed times the other r is r to the 4, dr d theta, and from here is a joke to end this. The answer is, dare I say, clearly 2 pi over 5. Yes.
So I get it with the terms of the circle, but so say, would there ever be a case where your first limits of integration there wouldn't look something like an equation full circle? So like if that was just a constant, what would you
No,
if you chose?
no, because it doesn't work with polar in that
Okay,
case.
all right, that was
Yeah.
that was kind of what I was wondering.
But they could be sneaky and give you different kind of different kind of just one quadrant in limits and so
I
on.
get that. I
Yeah.
was more curious
Well,
about
see,
what the direct transition.
you are not going to have an integral that it's not possible to do in polar, because again, this is section for polar integrals where the region has to be something that you deal with. Now, is everything for polar in a circle? No. We have those flowers. We have the cardoids. We have annulus. We have, right, all of these other shapes that your domain can take, not just circle. So any of those can end up in the limit. Now, the general formula for integration in double integral, it's for the polar coordinates. So this is your general region. General region for polar integral. Now our R, which is the inner integral, is allowed to vary. So now you're not going to have circles anymore. So we're going to say that our double integral R of some function f of x, y, dA is going to be given by the polar integral alpha to beta, and here is my g of theta, h of theta, and then function of r cosine theta, this is your x coordinate, and r sine theta for y coordinate, and you have to have your string r, dr, d theta. That doesn't change ever. So this formula here is the formula that is the general polar region. And with this formula, you can set up pretty much anything. Let's say that your stencil for making cookies, is a flower stencil. You're making a cookie that has 4 petals. What is the volume of the cookie that is above those 4 petals? So you have region region R equals, let's say that the cookies are 2-inch, let's go with 4-inch. So 4 cosine 2 theta. Four cosine 2 theta. I'm just going to quickly take a look at this. 4 cosine 2 theta. So 4 cosine 2 theta. That will graph as a flower extending out to 4, and it has 4 petals because you have 2 theta inside, and when number here is even, you are doubling it for number of petals, and when it's odd, you're keeping that number of petals, whatever the number is. Now guys, this is your XY floor, and the cookie is obviously right this part here on top. That's what the cookie is. So cookie is in the shape of the flower, right? Cookie is in the shape of the 4-petal flower, and there is some height to it. But what we are looking at here is the bird's eye perspective, right? The top view for those who are engineers. And I want to set up the integral for volume now. That's going to be a double integral. Now, whatever the function is for the top of the cookie, could be whatever it is, so I'm just going to keep it as f. And then I'm going to have r dr d theta. See, I need the volume of the entire cookie. So that's going to be 0 to 2 pi. This 2 pi over here is whole cookie. I'm not looking only for one petal. The full flower will be drawn as your zero goes from as your angle goes from 0 to 2 pi. And now, if you draw a representative d theta here, you'll see that it goes from 0 to the function 4 cosine 2 theta. There we go. I could have put blah over here, better than f actually, because it's whatever the top of the cookie looks like. Top of the cookie. That will be governed by some equation as well. Now these problems become really interesting fast. I don't know if we have the same definition of interesting, but I'm going to intersect two circles and put the XY axis here. And I'm going to go from -2 to 0 to 2 to 4. And I'm going to have the equation here as r equals 2. That's a circle, right? It goes through 2. And the second one over here is r equals to 4 cosine theta. So r equals 4 cosine theta is the circle that is shifted 2 units to the right. What I'm going to do now is I'm going to shade two different regions, different colors, and set up two different integrals for each color. Set up two different integrals. So let's work on orange shade. Let's say that your shape is above that domain, and you are looking for volume. So that will be orange integral, volume, double integral. Here is blah, because this is the top. We don't know what that is, doesn't matter. And then we know we have r dr d theta. I am going to draw my representative pizza slice d theta. And when I draw my representative pizza slice, I see that theta, d theta, is going to slide from this intersection point, which is angle alpha, to the next intersection point of the two, which is angle beta. So now, to find limits of integration, we solve two equals 4 cosine theta. Well, cosine theta is equal to 1/2, and that happens at theta equals positive or negative pi over 3. So now, there I say clearly, the outer limits are negative pi over 3 and positive pi over 3, because my representative pizza slice is allowed to swing from the alpha and swipe everything up to beta, and that will give you the entire region. And then your radius limits, as you can see, this the theta, the pizza slice, is always riding 2, right? So function 2, so the radius is 0 to 2.
It doesn't give you the full region, though, does it?
Why not?
You're cutting off a tiny little bit of the. You use those limits of integration, you're cutting off a tiny little bit on either side.
Do what? Okay, so this is a little bit tricky because you have no, you don't need two integrals. Your limits are from negative pi over 3 to pi over 3 because this is intersection of two functions. So okay, let me just, and then I'll write it down, and then it will be clear. So you have the limits of two functions, right? And when you subtract so I can draw over here another. You can't really see it. I don't know if I can maybe make it purple. I don't know. Another d theta in that little region right there. It is so that part is where you have the integral, not the integral. Yeah, I mean the pizza slice sliding on a different function, right? So this part over here, is r equals to 2. The small parts on each of the edges is the 4 cosine theta. So for the volume, for the orange, I have 0 to 2 on the radius, and that will give me the part inside between the alpha and beta. The small part here is riding a different function, so it's going to be the separate integral.
So you need two integrals.
Well, technically you need 3, but you can double it because it's symmetric. And it's if it's not always symmetric. So we're going to add another double integral of the same blah function, r d theta, and this one is going to be 0 to 4 cosine theta, and we need to double it because there are 2 of those regions. And now the question is, well, what are the limits for the angle now? Well, it starts at pi over 3, on the bottom, and it ends at pi over 2, because that's where you are hitting the 0. Cosine of pi over 2 is 0, and the radius ends up being 0, because you are swiping from, let me just make this larger, you are swiping from this corner here to this corner on the bottom, so your d theta is going to swipe between those two values. And the value at the origin has a radius as 0, and the value on top as the value as the where they intersect, which is pi over 3. So, and you have two of these regions. No. There we go. No. Good. And you have two of these regions to worry about. Now, the other one that I wanted to also talk about is this guy here, which is the blue, because you can shade either one of them. And now that one is going to be a single integral, and when you draw the representative pizza slice for this guy, you only worry about d theta, that it's in between swiping through light blue. So light blue integral v for volume is the double integral of, again, the same blah function, which is top, r dr d theta. The limits are still negative pi over 3 to positive pi over 3, because that's where it goes. And now this is what I like to say if you are struggling to set this up. The way the functions go is far minus close, and far is always the upper limit, close is always the bottom limit. So far minus close, far, there will be 4 cosine theta on top, and close is 2 on the bottom. Does this make any sense? Please note, it's hard to see, I did not color my representative pizza slice for light blue in the orange area, because this is the only, all of the pizza slice that I'm using for this region. It goes this way, it starts as a point, this d theta starts as a point, and as it goes from negative pi over 3 to positive pi over 3, which are limits, it will start widening and cover all of this, and then go back into a point on the other end. So you can see far minus close. Far is our 4 cosine theta, which is why it's the upper limit, and the close is r equals to 2 function. Now look, you're integrating in respect to r, so this is better be r equals and r equals. Over here you're differentiating theta, so it better be theta equals and theta equals. And you can't swap them in this case. So let's take a look at.
So you can or you can't?
Cannot.
Okay.
Cannot. They have another example in the book. I'm just going to briefly. So you have a circle, and then you have a 2-petal flower, and they want this region here. Clearly you have the same region on the other side. If they want just those 2 regions, then you just calculate one and double it. The formulas are, well, I should now draw the x and y axis, I guess. And the formula is r equals to 2 for the top one. And the bottom formula here, this one, is r equals 2 square root of cosine 2 theta. 2 square root of cosine 2 theta. So you draw the angle because your representative pizza slice, which I am only coloring in a region that it's necessary and operational. There we go. We can quickly set this integral. Volume is equal to double integral. I'll put blah again because we don't have the function that goes in here. R dr d theta. So whatever the function for the top, this is the top function. And now, if you are to set these two puppies equal to each other, you will find that this is, well, let's find. It's positive negative pi over 6. But let's go and calculate. So 2 is equal to 2 square root of cosine 2 theta. This is equal to square root of cosine 2 theta equals to 1. When you square both sides, you get cosine 2 theta is equal to 1. Cosine 2 theta, right? Yes. So now I have cosine 2 theta equals to 1. Now, where is the cosine equal 1? Well, it's equal at, cosine is equal 1 at 0, and then at 2 pi. Something is wrong here. It's not adding up. Oh, I wrote the problem wrong. This is not r equals 2, it's r equal to square root of 2. Holy nightmare. I'm going crazy over here to figure out what is wrong. Alright. So the inner circle is root 2, not 2. Alright, so now when I square this, I get 2 is equal to 4 cosine 2 theta. Cosine 2 theta is equal to 1/2. And that happens when 2 theta is equal to... So cosine is 1/2 when angle is pi over 3. So theta is pi over 6. And we see there is 1 below, 1 above. So negative pi over 6 to positive pi over 6 on the outer limits. The radius is the function close by, which is just square root of 2. And then it goes to 2 square root of cosine 2 theta on the upper limit. You all know that when you solve the basic integral, you had a, b, and then you had f of b minus f of a, right? So that's exactly what you need to think about now. Generally, I suggest students to think about far and close. So integral, close, and far. That's the way I envision it, because to me it's simple to see. This side is further away from the origin than the one inside. Therefore, it's going to be outer minus inner as I am moving closer to the origin. Does any of this make sense? We have time for another exercise, so let's do it. we're going to take a look at the problem 38, upper right. On a coolness scale from 0 to 10, this one ranks at about 17. Right? Look at that thing. It's not that it's just interesting shape, but it also has a hole in the middle. Right? So we use the polar coordinates to set this one up. And then we'll figure out what to do. So I don't think I can draw this. I can try, but I'm trying to draw this. So and then it's gonna go from here right there like that, and then it's gonna be abruptly cut, go in there, and then have the other one in the back. And we'll say there will be a hole over here going down and then exiting on the other end. Exiting on the other end. So this one goes, let's say goes there and goes this way. All right, good. And then I'm going to color this sign over here and say that that equation is z equals negative x squared plus y squared plus 8. And the other region, maybe we can put it in orange, is going to be z equals x squared plus 3y squared. And finally, the whole x squared plus y squared equals to 1. All right, good. No, leave it there for a second.
No, do you have the... Oh, never mind.
I copied everything. It looks terrible, but such is life. So, if I am to take a flashlight and put it above this object and shine the light, it is going to drop some kind of a domain over here. And that domain is going to have a hole in it. I need to know what these values are. It's a circle of some kind, better be, otherwise we're doomed. So to find those values, I am going to set the blue equals to orange, because z equals z. So negative x squared plus y squared plus 8 equals to x squared plus 3y squared. Hoping to figure out what these endpoints are. So as I move everything to the right, I get 8 equals 2x squared plus 2y squared. And finally I get x squared plus y squared equals to 4. Holy nightmare, it's 2. Nice. So now I know that this one is 2 and I know that this one is 1. So my domain are these two circles. The first one is at 1, the second one is at 2, and the material is going around. So it has a hole. Well, that's going to be nice for limits. So now I have my volume integral as a double integral. My scrolling is locked. There we go. So double integral. Well, let's start. There's no room, so I'll move it. Okay, so double integral. And I have the blue one on top. So this is going to be minus x squared plus y squared plus 8 minus the second one, which is x squared plus 3y squared. Guys, this is like an area between two curves, except now it's two volumes. So you subtract the bigger volume, which is on top, which is blue, minus the volume below orange one, and then the difference would be actually what's in between. R dr d theta. Well, actually I have to call this one dy dx for now because I have to convert it first. So this volume now, when I start converting, this is going to be when you add all of these, right? You have negative x squared is negative 2x squared, and then plus y minus 3 is minus 2y squared, and then plus 8 in parentheses dy dx. Then I'm going to kick out negative 2 in front of the integral. Note that I'm ignoring limits for rectangular coordinates, because we are just going to set up limits later for our picture. So I just need to get this nonsense out of the way. So I have x squared plus y squared, and then minus 4 dy dx. So what I have done is I took the upper equation minus the lower equation, because I need the upper volume minus the lower volume that I'm throwing away. And then I just did algebra, right? I am finally ready to convert this integral into the polar. Negative 2, double integral, and here is my r squared minus 4 r dr d theta. So this is what it happens. The conversion. I want the full circle. This shape is round, so 0 to 2 pi. And my inner radius is obviously 1 to 2, because it had the hole through the middle of 1, right? And it's extended as far out as 2. So now all I need to do is to clean this up, and in 2 steps I will have the answer. So volume is negative 2, double integral 0, 1, 2 pi, and 2. And over here I have r cubed minus 4r dr d theta. And now we start integrating. Negative 2 integral 0 to 2 pi. This is r to the 4 over 4 minus 2r squared from 0, no, not from 0, from 1 to 2, from 1 to 2 d theta. I still have to deal with that. Volume is equal negative 2 integral 0 to 2 pi. And now I plug in 2. 2 to the 4 is 16, divided by 4 is 4. Minus 8. And then I have minus 1/4. And then I have plus 2. All of that d theta. That's negative 2 integral. And now I work this out. So this is going to be negative 4, negative 2 minus 1/4. So that's negative 9/4. So it's negative 9/4 d theta from 0 to 2 pi. Negative kills negative, and 2 cancels 4, so I have 9/2. When I integrate theta, I get theta from 0 to 2 pi. 2 kills 2, 9 pi. Volume is 9 pi. Did any of this make sense? I'm going to run through this whole thing one more time. So we have the shape, and it's always our first order of business to set the two shapes one on top of the other, set them equal to each other to find out the fattest part that would cast the shadow the furthest away from the z-axis, the origin of the xy, to see how far it extends out. We do have hole through this one, and we know that hole is 1 because we have a circle radius 1. So we know that the hole is 2 inches wide, right? Diameter 2, radius is 1. So now when we do the algebra over here, when we set two shapes equal to each other, we find that the radius is 2. So if you have any kind of a hole anywhere that it's 2 inches in radius, 4 inches in diameter, this object will fit through it. All right. So this object is r equals 2 fat, right? That's as far as it goes outside. It's a radius, so 2 on one side, 2 on the other side, 4 inches wide as a diameter. Once we have that, we can go and set up the integral. Now, we had area between two curves earlier, where you said top function minus the bottom function, and then you have the area between two curves. Now you have the volume between two shapes. You have the blue shape on top and the orange shape on the bottom. When you find the integral of the blue shape, that gives you everything, all of the area extending all the way down to the red circle. You're getting all of this area, volume. All of the volume that you don't want, because it starts from the top and it takes all of the volume all the way down into the circle. There's no shape to it on the side. It's the orange one that shapes it. When you find the volume of the orange one, you get only the stuff you don't want. So when you have the blue one, which is what you do want, plus what you don't want, and you subtract the orange one, which is what you don't want, you get exactly the area between, which is why it's top function minus the bottom function inside the integral, just like your functions for area between two curves. This is technically volume between two shapes. So we do the upper minus the lower, and that was the problem, because we had to run all of these calculations in xy. So we ran all of these calculations in xy, and once we simplified it to this point here, we are ready to hit this with polar. X squared plus y squared becomes r squared. dy dx becomes r dr d theta string, which is always, I always put the blue, right, like that, 1 unit block, we just put it right there. And it's time for us to take the limits. The object is full, it's round, it's not chopped in half or something. It's full and round, so 0 to 2 pi for the entire shape. And then it has a hole, so we only take in consideration 1 to 2 because that's where the material is. In the hole inside of 1, there is nothing. If there was no hole, you would go from 0 to 2. Right? And then you just go and you integrate, and you're done. So that's the entire problem. I hope you're not disappointed. That's it. See you Monday.